Hello, thank you for watching this video. So in this video I'll be doing question 7 of November 2022 question paper mathematics paper 1. So I'll read question 7 and then answer its questions. So 7.1 read as follows. Determine f prime at x from first principles if f of x is equal to x squared plus x. Determine f prime at x from first principles if f of x is equal to x squared plus x. So they want you to determine f prime at x from first principles. What does that mean? Derive f prime at, they want to determine f prime at x from first principles. So they want f prime, which is the derivative of f, using the derivative definition. So, as you know, the derivative definition is f prime at x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. This is the derivative definition from first principles. So they want you to use this definition to find f prime of x if f of x, if given f of x equal to x squared plus x. So you are given that f of x is equal to x squared plus x. So they want you to find the derivative using the limit, the derivative definition. That's what they are asking you. So the first thing that you do, you can see here that you have a formula. Your definition said f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So you have f of x, that part. The part that you need to find is this one, f of x plus h. So f of x plus h is equal to, which means, if you're saying f of x plus h, which means when you see your x on f, you put it x plus h, which means here we have x plus h all squared plus x plus h. This is it. Then you simplify this. Then you say this, expand this. This is x squared plus 2xh plus h squared plus x plus h. So this is f of x plus h. Right? Now that you have your f, you have this, your f of x and your f at x plus h, you can go back to the formula, to your derivative definition, to substitute this. Sorry. So, from the derivative, from the definition, we have f prime at x is equal to the limit as h goes to 0 of f of x plus h, which is this thing here, which is x squared plus 2xh plus h squared plus x plus h minus f of x, which is this, x squared plus x, all divided by h. This is what you have. Then we just simplify this. F prime at x is equal to the limit as h goes to 0 of what? Of x squared plus 2xh plus h squared, right? Plus x plus h minus x squared minus x all over h. Like terms, this and this one cancel out. This one and this one cancel out. What are we left with? We're left with f prime at x is equal to the limit as h goes to 0 of what? Of 2xh plus h squared plus h all over h. Then you take out a common factor on top, which is h. f prime at x is equal to the limit as h goes to 0 of what? Take your h out, you're left with 2x plus h plus 1 all over h. And this and that goes away. What are you left with? You're left with f prime at x is equal to the limit as h goes to 0 of 2x plus h plus 1. Then you allow your h go to 0, which means we have f prime at x is equal to 2x plus 0 plus 1. Therefore, f prime at x is equal to 2x plus 1. This is your f prime from first principle. Straightforward. Straightforward. Then we go to the next question. Determine f prime at x if f of x is equal to this. So they want you to find the derivative of f. You don't have to use first principles now. Let me clean the board. So, this is 7.2. We are given that f of x is equal to 2x raised 5 minus 3x raised 4 plus 8x. So they want find f prime at x. So they want the derivative of that, right? So f prime at x is equal to derive this, so top times this, that is 10 x, then subtract 1 there, that is 4, right? Minus top times the coefficient there, which is minus 12 x raised 3 plus top here times this, it's 8 x raised 0, because subtract 1 in all of them. Therefore, f prime at x is equal to 10 raised x to the power 4 minus 12x cubed plus 8. So this is the derivative. This is the derivative of f. This is what they were asking. This is easy, and it's 3 marks. Very generous. Then go to 7.3. Clean the board. Let me use a different color. .3. I hope it's visible. Determine, 7.3. The tangent to g of x has a minimum gradient at the point 1 and 7. For which values of x will g be concave up? Let me read this again. The tangent to a function g, to a cubic function g, has a minimum gradient at the point minus 1 and 7 and minus 7. For which values of x will g be concave up? So you are told that the tangent at g has the minimum gradient at the point 1 and minus 7. For which values of these things concave up? Okay, this is what they're asking you. They're asking for which values of x will this function of yours be concave up. So they're telling you that the tangent to this function has a minimum gradient at this given point here. So what does this mean? So let's suppose that I'm just going to draw rough sketches of cubic functions. So let's say you have this cubic function here, right, where a is greater than 0, which means they said that g of x is equal to ax cubed plus 3x squared plus bx plus c. This is what they said. So let's say your a is greater than 0. So the shape of your function, just the shape, doesn't mean it's like this. Something similar to this. The shape of this graph. Right? But if I'll use another color. If a is less than 0, our function have this shape here. Something along the lines of this. Right? So these x coordinate of turning point, x coordinate of the turning point. So what you need to know is that the derivative of this function here is a parabola, right? Because if you derive that, the highest power will be 2. So it is a parabola. And this parabola that you are getting, gives you the gradient. Gives you the gradient at a point of give you the gradient of each and every point. So the derivative of a function gives you the instantaneous gradient at each and every point. Right? So if you were to draw the derivative, a rough sketch of the derivative of this function, you would find that it's something similar to this. So this one, something similar to this. So this is your a g here, and this should be a g prime, right? So if you look at it, look at this. At the turning point, at the turning point, the gradient is 0. That's what, and you see, because I said the derivative gives you the gradient of g. So you see the gradient is 0 here, and it's 0 here. Here the gradient is negative, is positive here, and you can see here the gradient function is also positive. Here the gradient is negative. Go from this after this turning point to here, and you can see the gradient is negative here. Here the gradient is positive. You can see that it's positive. So the derivative function, which is a parabola, gives you the gradient of this function. Similar thing here. So it will be something, so here, these are turning points here. Here is it here. So the gradient function is a parabola as well. But since a is negative, so it will have some shape along these things. Something similar to this. Similar logic is there. You can see here the gradient is negative, and you can see your function is also your gradient function, because this is your g and this is your g prime, this one here. So the g prime gives you the gradient of each and every point. So if this is positive, so the instantaneous gradient is negative, so it will be negative down there. So you can see it was negative going down here, and you can see here it's negative. Going up here, the gradient is positive. That's why you can see the gradient function there, positive. Going down here, the gradient, going down here, and you can see here, the gradient is negative, and so is the negative function, gradient function. So, what you are told here is that this function of yours has the minimum gradient, which means it has the smallest gradient. So, if you're looking at the gradient function of this one, this is the one. So, this is the gradient function. This one has is the one that has the smallest gradient function here, and this one here has the biggest gradient at that point. So So this one, this graph here has the minimum gradient, is the one that has the minimum gradient. Here is the minimum gradient. That one has the maximum gradient, which means the graph that they are telling us that we're talking about here is have this shape, not that one, because this one is the one that has the minimum gradient and that one does not have the minimum gradient. So we can clean this one and be stuck with the one that gives us the minimum, because this is the smallest gradient you can possibly have here. Then those ones you can see they are higher. So here, that is the largest gradient that you can possibly have. Then it becomes smaller afterwards. So this is not the case that we have. We have this case if we have the smallest gradient. Okay, so now you are told that the smallest gradient is found at -1 and 7. So you know the x value here is of the smallest gradient. This here is -1, right? So to optimize the gradient, okay, so the gradient function here, you will get it by saying, okay, the gradient function is the derivative of that one. So you say, okay, the gradient function, I'll get it by deriving that. So the g prime at x is equal to 3ax squared plus 6x plus b, right? That is your gradient function. And then now, if you want to optimize your gradient, you want to find the smallest gradient, right? That means to find the smallest gradient, which means you must optimize this further by deriving it, because to find the minimum or the extremes, the extreme values of a function, you must derive this one further. And you know, by deriving this, now you are getting the point of inflection, because you want to see where is this function of mine, where is this function of mine changing concavity. So you have the first gradient. To know, to find out where the graph actually changes concavity, you must derive this further. So you can say, okay, second derivative g prime at x is equal to 6ax plus 6, right? And okay, actually you don't even have to be honest, because you can see here, because you didn't even need this, you could have just worked with this from the beginning. So you can see that your function, your maximum gradient, your minimum gradient is at x is equal to -1. That's what your minimum gradient is, and that minimum gradient corresponds to your point of inflection, because you will get that minimum gradient by deriving further. That's what I could have said from the beginning. So to get this minimum gradient here, you will find it by deriving this one further. So it was found, this value here was found from the second derivative of the gradient. So this is the point where the point of inflection is. Therefore, you will get your point of, your graph will be concave after when x is greater than -1. This is what that means. So you didn't need this, to be honest, because they've done that already for you. To get the turning point, or the point where the minimum gradient, the x value where the minimum gradient is, which means that they had already derived your gradient for the second time, which means to find the point of inflection, which was at -1. So this will be concave up for x greater than -1. At least I think so. Or you can write it the way, easiest way, x an element of -1 to infinity. That's the way of writing this. So we're done with this question. Go to the next one. But for this one, I will need more papers to draw the diagram first. So I'll need to buy papers because I don't have papers yet. Thank you for watching. I hope this is clear. We didn't need this at all because, like I've explained, there's nothing new that I can explain.